Hello and welcome to this presentation of StruSoft Prestress 6.4. In this tutorial I will be showing you one element and that is a double T element and the calculation of it. I will be using normal standard Eurocode for this example. And in the program the first thing that meets you is this project manager. Here we will be entering the name or identifier of the element, the length, and this is the total length of the element. And if we have other elements in this file, as it is possible to have multiple elements in each file, it could be possible to have a list with the previous entered sections here. But since this is the first file and the first element of this file, I will just use the cross-section database. Here we have two different sets of databases. One is called non-standard concrete, and here the user can store all their own cross-sections, while we in the standard Eurocode concrete have a specific setup of sections provided by factories and producers. In this example I will be using a variable T section for my double T element, and I will be selecting this. As you can see here, we will only be looking at one particular leg of this double T element, but that is only to make the calculation a little bit better. When we have the identifier, the length and the section, I press add, and this will bring up a wizard, and this wizard we will be able to calculate the dead load automatically, and that I have to make a load case for. So I will be adding a few load cases here, like dead load. I will have live load on the element, and it's also, as you can see, possible to add all the different kinds of load cases as you will be having in this example. So I will be adding a topping as well, and this topping is a non-structural topping, so it has no interaction between the element. It's only treated as a load. And I will have a set of installations or ventilations in the attached to the element. I select the load case, in this case dead load, and as you can see it now will automatically generate the dead load and add it to the dead load case. I will be able to automatically create a set of load combinations according to the current code settings. And this is load combinations like release, storage, transportations, erections, and different sets of short-term and long-term load combinations, and a couple of ultimate limit states as well. The program will automatically create supports according to the current code settings as well, and it is recommended to use this setting, and if you want to change the supports or the location of the supports, we will be able to much easier change already existing support than to add a new support. When we now accept the wizard settings, we can now see here in the list what kind of identifier, the length, and the section we have. And in this list, if we have several elements, then that list will be filled up. To the left, we can see the project and a tree setting here, where we have the element and a set of sub-branches for each load combination. Each load combination will be dependent on the previous one, which means that we will be taking into consideration all things that has happened to the element in previous stages. So for instance, if we would have a crack in the release stage, that crack will be present even if it is closed in later stages. So if we would get any deflections, that might open this crack. And the program can recognize if it is in the top or in the bottom. So we will be going into the next step, and that is to see the reinforcement of this element. But first, in order to set the correct covers and so on, we will be looking into each load combination to see the exposure class, the life length class, and the material properties for each class or for each combination. So I will be continue down to release, and this is the release in the factory, where we have the release strength of the concrete. The exposure class and life class is not that relevant in this case, since the time spent in the factory is very short. And that is also the case for storage and maturing, which is a load combination aimed for the storage at the factory before the transportation out to the construction site. And as we can see here, the strength class of the concrete has been improved from 3037 to 3545. And we will be continue to transport. Same here, the concrete class has been automatically set a little bit higher, but it's up to the user to actually set the correct strength class for each load combination. We have the erection of the construction site here, and then comes the different kinds of stages. Like this is an intermediate stage, a short-term stage where we actually will be loading the double T element with a short-term load in order to get maximum cracking into the load combination here, called final stage long-term. Here it would be good to set the exposure classes for the final stages, and also for the final stage short term, where we will be seeing the load combination set for the maximum deflection. We have two ultimate limit states generated automatically in the program, but it's also possible to add a few more, like fire load case and so on. We go back to the element and just take a little peek into the reinforcement details. Here it will be possible to see the code settings, what minimum cover I need, or the minimum distance between bars I will be needing. And in the left column here, I will be able to set the cover that I want to use for this element. So it is possible to step aside from the code, either if you would be looking at the older element that has not been calculated according to the current code, but also if you would have any set of actions that would be able to change the settings for this. We go back to the main reinforcement here, and with these cover settings it is possible now to add reinforcement bars, both pre-stressed and non-pre-stressed wires and bars. I will be using a command here called layer of reinforcement, and in this setting I have the ability to set with a cover, a diameter, and the material. And here I have the normal reinforcement bars, and I have a set of 2 wires. One is the standard and one is a super 7-wire strand. And I have the possibility to have a top and bottom, and I can also set a cover inside here. I say that I have 2 reinforcement bars in the top, and as you can see they will be displayed here in the left figure, and in the bottom I want to have 4 in the bottom layer and 4 in the second layer. It is possible to add as many layers as possible, and if you would like to remove any layer, just press 0 and it will be removed. I will accept these settings, and as you can see now the list has been filled up. The coordinates is where the reinforcement bar or the pre-stressing strand starts, and that is in the left end here with the x-axis alongside the beam, and the y and the z-axis are in the cross-section. The length of the bar is automatically generated to find the end of the element. I have the diameter here set from the previous dialog, the area, and the pre-stressing. The full bond is only a function that currently works in the sloped I-beam, but it is still present in this dialog. And here it is possible to change the material if you want to change it. If one of these wires would be set outside the cross-section, it turns red, which means that it will not be considered into the calculation. And this is not only inside but also in length. So if I would enter a 15-meter long strand, it is extended outside the element. The next step is to look at the stirrups, and here I will be setting up a set of stirrups, and I need to start at the 0. If I would start 40 millimeters in, then the element would think that it is not reinforced at all between 0 and 40 millimeters, for instance. So it is recommended to set it at 0, which means that the whole beam will now be reinforced with stirrups. It is not possible to overlap the a group of stirrups. So if I want to have different spacing, I need to define a set of stirrups like this. This starts at 1000 and it has a spacing of 300 and it is 10 meters long, diameter 6. The next is 11 meters and it will be enough to have it fully at 12 meters. The reinforcement details, we are not going to change anything at this stage. The calculation settings is a setting for different kinds of calculations, and the most important here might be if you want to make the shear calculation using the shear reinforcement according to Eurocode 2 chapter 623, or without the shear reinforcement according to chapter 622. We will be using the shear reinforcement for this calculation. Here is the tab for the fire, and we do not have any fire set for this particular calculation. It will be shown in another tutorial. And the calculation sections, and these are the sections where the program will be making the calculation, and these are not the sections where the calculations will be shown or the results. And it is important here to have a good spacing between the sections, but as a first setting the program will automatically generate these. So it is only good for the user to go in and verify that the 2D element mesh is okay. The next step will be to go into the loads, and for this I will be changing into the load combination dialog here, but I will also change the input in the top left corner here to input loads. I will minimize the window here by pressing the 2 yellow arrows, and it is possible to extend it again by using these 2 arrows again. As you can see here now, we are in the load case called dead load, as seen here in the top right. This is the load that has been automatically generated on the beams, so we do not have to add more dead load in this case. As for the installation, we have a load of 0.5 kilonewtons per square meter, and the beam here that we are looking at is 1.2 meters wide, so we will be adding a load of 0.6 kilonewtons per meter. We will be adding this installation from the erection and forward, because it's at the construction site that we actually see these placed on our element. So I will be using the uniform load, and I will enter 0.6 kilonewtons per meter, and I will add it to the element. And this load will be present for all the later stages as well, which means that I have to add it like this. The next load case is the live load, and this is a storage that we're looking at with a load of 8 kilonewtons per meter and times the load width of 1.2 meter, which means that I have a load of 9.6 kilonewtons per meter. And this load comes from the intermediate stage and forward. The last one is the topping, and we will be looking at a 50 millimeter thick topping, and it's treated as a permanent load, and 50 millimeters times the density of the concrete and the width of the element, which means that I will have a load of 1.5 kilonewtons per meter. And this load will be present from the construction site, or the erection phase here, since this topping will be wet in that case. And that is the loads. It is possible to get an overview of all the loads by just pressing the load combination here. I can see that the topping starts now in the erection phase and will be present in all the later stages. The live load will be added into the intermediate stage and forward. And the installation is from the erection stage and forward. I will now expand this window, and we are now in the load combination phase, so I will be adding the different load cases into each load combination. I select the first stage, which is release, and I will be adding the dead load in this case and press change. As you can see here now, we see that in the second ID, which is the storage maturing, it will be dependent of the first one. So this is the dependency backwards that we are calculating with in this program. And for the transportation, for instance, I might have a dynamic factor of 1.4, and I will change this, and this is only to simulate the dynamic effects of the transportation, the lifting with the cranes, and so on. I have the erection phase where I have the dead load, I have a topping, and an installation load. If you would have any other kind of load, like people walking or something like that on the element, we could change the or add a live load in this case, which would be a little bit smaller than the current live load that we have, which is 0 for the erection phase at this stage. As for the intermediate stage, I will be having my dead load, the topping, and the installations. Those are permanent, but I will have the live load with a C factor of 0.7. This value here is actually the same as in the final stage short term. So here we have the dead load, we have the topping, we have the installation, and we have 0.7 times the live load. As for the long-term load, I have the dead load, topping, installation, and 0.5 times the live load. For this particular case. Then we have the two ultimate limit stages, and these are the one where I set 1.35 times the dead load plus topping and installation plus 1.5 times the C factor of 0.7 times the live load. And as for load combination 610B, I will be using 1.35 times 0.85 times the dead load plus 1.35 times 0.85 times the topping, and so on. And it is possible to add many of the parameters here in this case, and I have 1.5 times the live load. As you can see now, the program doesn't show the whole line here, but I can make this shorter by unticking the original text to actually see that the program combines it into settings like this. It is also possible to go back to the original text if you want to see where all these parameters come from. When we go into the long-term parameters, we will only be adding the differences between the previous calculation and this load combination that we're currently standing on. So for the storage and maturing, we have the creep coefficient of 0.5, and I have an even shrinkage of 0.2 per mil. As for the final stage long term, here I will be adding the difference from the storage and maturing to the final stage, and the difference is 1.5 here, and it is 0.2 in the shrinkage. And this means that we will be calculating with a creep coefficient of 2 in the long term final stage, which is the sum of the previous ones and the ones that we're looking at. That is the long-term parameters. We will now be calculating, so let's just press calculate here in the top, and I select calculate. All these settings are default settings for the program to calculate correctly, so we do not need to change those. And the analytical result that we see here, we have the moments, and we can see in the intermediate stage short term and the final stage short term that we have the same moment due to the same loading. But if I go into the deflections, for instance, we can see that the deflection, which will be shown here, is shown by two numbers. The first one is the shortening of the element to that point, and the second one is the deflection upwards or downwards that we're looking for. So for the intermediate stage short term, we can see that we have 17 millimeters of camber, while we have 19.9 millimeters of camber in the final stage short term. We can also see that we have deflections in the final stages, the ultimate limit stages, but these can be ignored since we are looking at the ultimate limit stage parameters for the materials as well, so these are heavily reduced for the deflections. If we go into the design, we can now be making the calculations for the design, which means that we will now be checking for the code, and we see that we get a few errors here, and these errors are the minimum reinforcement. We do not have enough minimum reinforcement in this beam, and we can also see with red here that we are exceeding a few settings or calculations according to the code. So in order to see what is happening here in the storage and maturing, I will be going into the result utilization table, where I can see that the utilization here is 180%, while the ultimate limit stages, they seem to be okay with 95 and 83%. So I go into the result, I go into the code check, and I go to my case here. And here I can see that the compression stress, it is too high for this element. So in order to fix this, we could either have fewer reinforcement wires in the bottom. We can increase the strength of the concrete, or we can reduce the pre-stress. So this is not okay, but we can see that all the other cases are okay for this stage. And in this case, I would go back to the geometry, go back to the storage and maturing, and either set the strength class a little bit higher. And here comes an option with prevention of longitudinal cracks can be avoided, which means that we can use the concrete stress a little bit higher. So I will be activating that one. But as we could see with the ultimate limit stages, we had 95% utilization. So I will just see what happens if I reduce the number of strands here from 4 to 2. And I press calculate. Go into design, calculate. Yes, now we have still the problem with the minimum reinforcement. As can be seen here, the storage and maturing, it is okay, but we now get red values here for the final stages. And that means if we go into the result, code check, and check in the final stages, we will have checks of the shear capacity, the moment capacity, and so on. And with the reduced pre-stressing, we can actually see that the shear capacity is now a problem. And then we go into the table bending to actually see the stresses that we have, and we can see that we have a crack stages here as well, so the element is most likely being got some cracks here. If we look into the final stage, we can see that this is only due to bending, and the bending seems to be okay, which is the utilization between the moment due to the load and the ultimate limit strength. If we go into table bending for the serviceability limit states, the column here on the far right, that is the deflections that we can see, and positive is camber, while the negative values are deflection downwards. If we go into the results and table shear, the shear calculations is only being made for the final stages, and here I now can go in and see the shear force due to the load. I have the shear capacity, I have the ultimate or the utilization between the shear force that the program will be using to reinforce with compared to the capacity. This is the maximum capacity before we get web compressive failure. Here we have the current amount of reinforcement. This is the required reinforcement due to the loading, and this is the required reinforcement due to the code minimum requirement. And as we can see here, we have a required due to load in 1.2 meters. That is both higher for the requirement and the minimum reinforcement than we actually have in the beam, which means that it would be good to increase the current amount to at least 224 millimeters per square meter, while we have only 188. So go back to geometry, go into stirrups, and let's see if we can 226. It should be okay. I make the calculation. I make the design. And it is now seems to be okay in the 610A, but not in the 610B. Let's see the utilization table, and yes, not enough. As you can see, it is 1.3% above. And we go into the code check to see what is happening there. Yeah, it's the shear as well. But if I would go into the table shear for this stage, we can now see that it is okay in all stages. But in 610B, we still have a requirement of 230 due to the load, and I have 226, which means that I would most likely go back and increase either the length of the first group and shorten the second group, or increase the amount of stirrups in the second group. The final result that we will be looking at is the cracking, and we can see here that this element gets some cracks early in the release stage in the factory, and we can now see that it goes into crack stage 2, and this means that I have a distance between the cracks here, and I have a crack width that I can look at. So this is not concluding the design, which means that I would most likely go back to the reinforcement and check my shear calculation, but it concludes this tutorial. Good luck.